Recording in progress.
Okay, so anyway, as we look at this here, the first derivative is really easy. We found that. You could take the derivative again if you like, and you get that. As a second derivative, third derivative would be that, and so forth. The corresponding notation for the second derivative in dy over dx notation looks like this. That kind of makes sense, right? Because dy over dx is a derivative, and when you do the ddx of the derivative, if you're doing a derivative of a derivative, what do you call that? Second, yeah, exactly, right? So this right here is what we call the derivative of the derivative, or the second. So if you see that symbol, just, or that thing, just assume that's what you're asked to do. Or you can write like this. This is kind of a popular way of writing it. I know it's a little weird. Looks like you're squaring, so you're not really squaring anything. I know it looks a little funny. But what it means that you're doing the ddx twice. And it's kind of weird, but it's not x is being squared. Actually, the dx is being squared. It's kind of weird.
You put parentheses then around dx?
Not really, we don't. It's just the way it's written. So, I mean, if you did, I don't think that's bad, but anyway, yeah. Okay, so that's what's happening there. Calculator work, how to check your derivatives in the calculator. So we found this earlier, right? Example 11, which was a while ago. The original function was that, the derivative is that. How do you know you did the derivative correct? I think I kind of showed this to you guys already, but I'll do it again. So you can graph the original function, graph the derivative by doing d dx of y1, and do x equals x, so it actually graphs the derivative for you, and then do the derivative found by hand as y3. You could change the graphing style with a thicker line or thicker curve for y3. So y3 should trace y2. If y3 does not trace y2, it looks totally different, then you know you've done something wrong. Either you've typed in something wrong, that could happen, or maybe you found your derivative wrong. But at least you know things are somewhat awry if they don't trace over each other. There's a way you can kind of check your work. So I think you guys get the idea. We don't have to do it, but I just want to explain that because I think we kind of did that the other day. But that's what you would do. You could do that to check your work. So and then if you could adjust the window, sure, whatever, adjust the window. So that's what's happened there. Okay. Now let's talk about 3-4. Let's see how far we can get today. Okay, so we're going to talk about application of the derivative. This is probably the most popular application, linear motion, physics, right? A lot of physics happening here. So if you think about distance, fine. Change distance or change of time is usually velocity or speed. More specifically, it's going to be the change of position over time. So we'll talk about that. And I'll probably try to do my best way of emulating these things. I'll kind of like walk back and forth. Oh, thanks. To kind of show you the difference between position and velocity and all those things. Oh, thanks. Okay. So average rate of change, you know what that is? Also can be written as this way, a plus h minus fa over a plus h minus a, which does reduce to h on the bottom. Guys, quiet. Instantaneous rate of change is a limit notation, right? A limit definition. Okay. All right. And Jaden and Olivia, thanks. All right. So derivative f prime of a is called instantaneous rate of change. So y equals fx with respect to x when x equals a. Now, instantaneous doesn't necessarily have to represent time, just so you know. We still use it regardless. So x doesn't have to represent time. So, for example, it could be find the rate of change of volume versus the radius, things like that. Oftentimes we omit the word instantaneous and it's just assumed. So if you're asking to find the rate of change, it's usually you're assuming a derivative. If you do want average rate of change, you'll be explicitly told that, just so you know. If I want an average rate of change, the word average will be next to rate of change. If you're just told, hey, just find the rate of change, you can assume it's a derivative. So for example, number one, how would I write the volume of a sphere as a function of its radius? Well, I know that. That's, well, maybe you guys don't know. You guys know what volume sphere? It's on the SAT. Yeah. They give it to you on the SAT, by the way. You don't have to memorize it. But I'll never ask you to memorize the stuff. So don't worry about that. But 4/3 power cubed. Now, find instantaneous rate of change of volume with respect to R. So basically you're doing this. When it says this here, of volume with respect to R, it's written like this, dV over dr. So when you see that, that's assuming you're doing a derivative with respect to R. The whole respect thing, like, well, respect to what else then? That will matter if we deal with a formula with 3 or more variables. Give me a volume formula that has 3 or more variables. The size of the sphere. Give me another solid that could have like multiple variables. So how about a cylinder? Right? Or prism. Yeah, you say in base, but let's talk about cylinder. What's the volume of the cylinder? Pi squared h, right? So I could do the volume of this. I could take a derivative of the volume of the cylinder, but with respect to what? I could do it with R or with H. And that's something that we won't talk about. Actually, we get right up to that point when we finish this calculus unit. You will do that in the fall with AP Calculus BC.
Wouldn't that just be the same as like a circle though?
Not quite, because you're gonna have to substitute one of the variables. Okay. Not quite. But that's why the word respect kind of matters a little bit. But for now, you only have one variable, so you know to do that derivative. So what's that derivative, guys? 4/3 pi times what? Now, I'm going to kind of show this to you guys right now. There's kind of a phantom expression next to it. Okay. You will see this in the fall. But when you have R cubed, right? The 3 moves to the front. You brought that by 1. So where does the extra R go? Where is it? It's actually over here. dr over dr. Of course, when these are the same, top and bottom same, what do you assume it is? 1, right? But what if I took the derivative of this with respect to a different variable? What if I want to take, I mean, let's say I'm just making up a variable. Let's say I call it x, right? Sure, take derivative of R cubed, which is 3R squared. But then you have to put dr over dx. Because what you're doing as an operator is you're taking the derivative of both sides with respect to a variable as an operator. So when you have R cubed, when you take respect to R, what you're doing is you're doing 3R squared, great. But then you have to say, oh, but times its differential, which is in this case dr over dr, or in this case dr over dx. But we're of course doing it with R, not with x. So if I do that, so we don't show it because it's kind of redundant, but just something to be aware of in a few months. Ethan, go ahead.
Wait, but like, why would you put dr over dx in the first place? Or do you what x isn't in the equation?
I know. I'm just being hypothetical.
Oh, okay.
That's all. Yeah. You will actually have to deal with this when you deal with like circles or like shapes that have like x and y is not necessarily by itself.
So we specify like which variable you need derivative.
Correct.
Okay.
Now in this case, let's actually find the rate of change of the volume at various values. So let's say I want to find dv over dr r equals 1. Oh, I didn't clean this up, by the way. We clean up, what do you guys got? My apologies. 4 pi r squared, right? Which, by the way, is surface area. It's not a coincidence. That's surface area. There's actually a very strong kind of calculus connection with all these solids and areas and volume, but that's stuff for a later time. If we work this out, you get 4 pi. Please state the units. If I'm looking at change of volume, what would my units be? It's kind of tricky. Per centimeter. Yeah, it's kind of weird. Because you're looking at the change of the volume versus the change of the radius. There's actually a slope. That's a change, because that volumes are y and radius is your x, right? That's a change y or change in x. That change in volume or change in radius, right? Or if I plug in for 3, if I want v prime of 3, $36 pi? Yeah, 36 pi. So you get that. Okay, we're good on that? Okay, so let's now talk about linear motion. Okay, position. So position is just simply where you are from your starting point. So suppose S is measured in miles and T is in hours, and the graph S is against T is drawn, and the slope at T equals 2 is calculated. What are the units of the slope? So I'm going to just kind of draw kind of something crazy. I should just do it to a color. Okay, so you think about the slope. What would the units of the slope be? So what's my y represent? Per hour, right? Looking at change in miles and change per hour, or miles per hour. Right? So the slope at 2 represents instantaneous rate of change of the position function with respect to time t. We also call it the instantaneous velocity at t equals 2. So to see, excuse me, to see this, you can use t for 2 and then t plus h, something close to 2. And if you take the slope, it's the same thing as that. But if you want to add, that's average velocity, right? If you want instantaneous, then you have limits. It's got to be derivative. So ds over dt is the same thing as velocity.
The instantaneous velocity would be different than if you just took like y over x.
Well, if you could the change of x is average. Like say you're driving from here to LA, you take the total distance divided by total time. That's average.
Oh, but it's the
But it's at a moment. Like say right when you hop on the highway 101, fine. Then now you're going 80 miles an hour. Right. Yeah.
How's that any different from like just doing y next though?
Well, sorry, say what?
Was that any different from just using y next? That's variable.
y over x.
Y over x.
Like dy over dx.
Right, but the thing is that if you have dy, well, no, well that it is dy over dx. It is. Well, I'm just giving you context.
Okay.
It is dy over dx. It is. It is. Yeah, actually, just to reiterate, what's my y here? Position, or miles. What's my x here? Time. Okay, let's keep moving. So let's say we have this graph here. Now another thing to keep in mind: what if I graph velocity? So can you guys? Thanks. All right, I'm trying to. All right, thanks. All right. Okay, let's draw a little better. I don't like that.
So that's a derivative, right?
Okay, let's just do that. Here we go. Okay. So how about this one? Okay, what's the use for this? Wouldn't that be the change in miles per hour over hours? Yeah, miles per hour squared. Look at you, the AP Physics student. Right? AP Physics? Good. All right. Miles per hour squared. This represents acceleration. So you're asking why we need second derivative. That's precisely it. So I'll be the acceleration. So you can think of it as dv over dt or dds over dt. Sometimes we also write it as trying to think here. I guess you could write like this: v of t plus h. Actually, limit notation. The limit is h put to 0 of v of t plus h minus v of t. Hi, Marcus. Over h. And by the way, velocity can be positive or negative, depending on the direction of travel. So, say for example, we'll consider north to be positive, south to be negative. And I kind of joke about this. Anyone know the speed limit of El Camino? Like right around like where the Target is in Redwood City, Menlo Park, 35. And sometimes there's a cop there. If you go 50, you will get pulled over. That's happened to me.
50 and 35.
Well, El Camino, there's like no cars. Okay, like at 7 o'clock. I don't know. If I'm here working late, I don't know. Okay, well, or I just try crazy, I guess. Well, point being,
Friends are like, yeah, but El,
well, that's worse of Valparaiso because that's people walk crossing. Well, well, people do cross El Camino too. Okay.
Nobody goes to speed limit.
Okay. The point I'm trying to make is that it's speed, not velocity, right? So if you're trying to be a smartass to the cop and you're going southbound, and he's like, well, you're going over this, it's say you're going 50 miles per hour southbound, but really going negative 50 because that's south direction. He said, no, I'm not going over 35 because I'm going negative 50. I mean, he's going to give you a ticket because you're being a smartass. But the point being is that you see the difference between velocity and speed, right? Because speed, direction doesn't matter, right? Because speed still kills. That could, you hit something, you're gonna hurt yourself, kill somebody, right? But velocity obviously involves direction. We're going to talk about that in a moment. But speed is the absolute velocity. So that's why they call a speed limit, not a velocity limit, because velocity limit could be your interpretation of what you consider to be positive or negative. So it just depends on direction. Speed does not, just so you know. So don't use that velocity excuse for the cop. They will still give you a ticket. And by the way, if you ever get pulled over, apologize and be calm. You might get off. I've actually talked myself out several tickets over the years. So, yeah. But insurance is bad too, because you have to really. But apologize. Always own up to it. And don't go too fast, because if you go really too fast, they'll give you a ticket. All right. Anyway, how do you think I'm going to do this here? How do I find the? Are asked to find position? Yeah. Okay, position. So we use the letter S for position. I don't know why, but we do. So what's going to be the position at 1? Yeah, 4. And we don't have units, so don't worry about. Do we have units? Yeah, don't worry about units. So 4. Let's just say 4. Where are they? Oh, I do see it. Then we do care about it. Okay, never mind. So 4 meters per second.
Is this like the double derivative thing?
Not yet. We're getting there. So we're just doing position right now. We're not even doing derivative, not even doing any calculus. We're just plugging into the position function. Sorry. So when my brain starts thinking too fast. I drive fast and I think fast. Okay. Okay, 4 meters. Yes. Thank you, Lynn, for catching that. What about 2? Yes, 2, right? What about 3? 0. And position is defined as like where you are from a certain place. Like let's say you're leaving your home or leaving Sacred Heart, let's say. So we'll define that as like the initial position will be here, Sacred Heart, right? So your car's parked right outside, that will be 0 position. S of 4, what would that be? 4, good. Okay, now displacement, that's a big one. Say, for example, so actually Mr. Donahoe's really good at doing this. He can actually go back from here to Pete's Coffee. So Pete's in downtown Mill Park. He could do it in, I think, like 6 minutes. It's kind of crazy, actually. Drive again. Yeah, they're back. Yeah, he orders on the app. He gets his coffee, comes right back.
Nice.
So, but here's a question: what's his displacement when he comes back? 0, exactly, because this is a starting point. But what was his distance? Probably maybe a couple miles, because it takes a mile to get there and a mile to get back, right? Or on the odometer, obviously the odometer doesn't measure displacement, measures distance, right? So displacement is more the change in position. Distance, of course, is the total distance you traveled, right? So I want to make sure we also have that distinction as well. So if you think about it, when you look at part E, what is the displacement for the first 4 seconds? That's going to be 0. Because you're doing S of 4 minus S of 0. 4 minus 4 to 0. We also like to call it delta S.
Not S of 1.
First 4 seconds from 0 to 4.
Why is it called delta S? Is that just
The change in S, the change in position.
Yeah.
S is position, delta S is the change position.
S of 0 is 0.
Oh, you're right. Wait, no. Wait, oh, you're right. Sorry, guys. I'm making a lot of careless errors. See, you guys are paying attention on a Friday afternoon. I appreciate it. Yeah, what's S of 0? My apologies. S of 0 is what? Yeah, my apologies. My bad. Okay. But what's my change in position from 1 to 4? Okay, I was right about that. All right. My apologies. Okay. Sorry for the confusion there. We're okay at that? Cool. All right. Okay, I'll try to slow down a little bit. Average velocity. Okay. That's going to be S of 4 minus S of 0 over what? Over 4 minus 0, exactly right. So it's going to be the change in S over the change in T. When you see this, that will always be average velocity. Because on average, for example, say you're leaving from Sacred Heart, you're going, actually, we'll do this. This is a good example. So I'm going to Kairos next week. I think we're going to like San Juan Bautista or somewhere in Salinas. It's about 100 miles. Okay. Was that? No, we didn't know we're going. Yeah. You're not supposed to know what happens there. That's, you know where you're going. You know where we're going, Jaden? Exactly.
I didn't know until that.
Yeah, now you know. Okay. But let's say it's 100 miles, right? To get from here to Salinas. And you take 2 hours to get there. What's your average speed? 50 miles per hour. But are we driving 50 miles per hour the whole time? No. No. I am driving, so I gotta be careful. But I mean, maybe I'm going 70 miles an hour, 75 miles an hour. But on average, we're going 50 miles an hour, right? So in this case, that'll be 4 over 4 or 1 meter per second. Now, Jane, you probably don't want to drive with me now, right? Because I drive too fast. Yeah. I do have a perfect record though. I go to traffic school of driving. No, I get tickets. I get lots of tickets. But I go to traffic school. I go to traffic school, get off my record. Because you get it off your record when you go to traffic school.
Oh, how often do you?
Every 18 months. You're allowed 18 months. After 18 months, you get a ticket. So, and somehow I've faced not like I'm doing delivery, it just happens to be that way. So
You had to really tell me total tickets.
oh, we can look it up right now. It's in San Mateo County. If you look it up. Yeah. Oh, it's public record. Anybody in this room. I can look at it. Yeah. Just go to County of San Mateo Traffic Division, and then you have to put my full. No, for myself. I just
Can we check?
no, to make sure I don't get screwed over on my insurance, to make sure it's clean. Because my insurance go up. These are all adult things you gotta pay attention to. Oh, I see one's going there right now. But you have to put my full legal name. So
Oh,
all right. Anyway, let's keep moving here. What's instantaneous velocity at t equals 4? Now, what was my function again? S of t was what? T squared
times t minus 3.
t minus 3 squared. Okay. Actually, let's write out the full expanded form. What was the expanded form? Plus. Okay. So let's try this again. So t cubed minus what again? Plus. Okay. So if I do s prime of t, which is same as v of t, what's that going to be? Perfect. Now let's actually plug in 4. And by the way, before I do it, take a look at 4. If you drew a slope at 4, is that pretty steep? Yeah. I expect a definitely positive number, a number that's fairly large. So if I do s of 4, sorry, v of 4, I should get 48. I think I got 9. Is it 9? Yes, 9. That's 9 meters per second. However, what was the average rate of change again? Do you guys see that difference? That blue line is a secant line. That red line is a tangent line, right? The red line is a tangent line. That's 9. You find that slope by doing the derivative of position. That's average rate of change. That's just the slope of the position function. So what would it be at 2? Now 2, wouldn't I expect that to be a negative tangent line, right? Yep. So I've got to do v of 2 or s prime of 2. That's going to be 3 times 4 minus 24 plus 9. That should be negative 3, I think. Yeah, I should get negative 3. It's negative 3 times 4 minus 24 plus 9. What's the speed at 2, though? Right, exactly. So if you told the cop, no, I was going negative. No. Your speed, absolute value of velocity. So what this means is that if I'm going to graph speed, I'm going to have to make sure my graph stays above the x-axis, right? It's going to stay above the x-axis because it's got to be positive. Let's sketch this. That should be pretty easy. Let me think here. I can factor out 3, right? Can I factor this more? So those are my x-intercepts, right? 2, if I plug in 2, well, yeah, we knew it was -3. The y-intercept was 9. F4 is also 9. That's just using symmetry. So there's my velocity function. Okay. So the sketch, obviously I've done. Where does it change direction? What do you think? T equals what? Where? Because remember, velocity, if velocity is positive, you're going one way. If it's negative, you turn around 180. That's actually, it's gonna be at 1 and 3. Because the velocity is 0. Because when you're in, you know this, when velocity is 0, what do we say that is? We're at rest. Yeah, sorry, I didn't make my question very clear. But what does that mean to be at rest? You stopped. And usually you'll change direction. Or you just go in the same direction again. So t equals 1 and t equals 3. That's when velocity changes sign. This is huge because we gotta look at where the derivative changes sign. And we'll use sign charts for that.
So like as it's getting closer to 0, the speed is slowing down, and then it's going backwards when it's negative.
Right. Yes, we're gonna talk about slowing down, speeding up in just a moment. Yes.
So does it change directions also at the vertex?
No, the acceleration will change. Actually, this is another great question. And this is for those who are going to take the driver's test, because I think they ask you sometimes like braking distance, like you're driving 40 miles per hour. And by the way, you guys should know this. If you double your speed, how does it change your braking distance?
I don't know. Wait.
Nothing.
Charlie, what do you think?
Sorry.
If you double the speed, what do your braking distance? It quadruples.
Bro.
It quadruples because it involves v squared. But I don't, that's, anyway, that doesn't really apply to this here. I just want to ask that question because I feel like asking it. Yes, it's 1/2 mv squared, right? Yeah, kinetic energy. But anyway, the point I'm trying to make is that when you hit the brakes, are you still moving forward? You are, right? Even if you see a car in front of you, slam the brakes. Let's say you slam it and like you hit the person in front of you. Of course you move forward because you hit the person in front of you. But you're slowing down because you're decelerating. So we're going to talk about acceleration velocity in just a moment. But if you do, when you do hit the brakes, you're still, even though you're slowing down, the acceleration is still going to be, the acceleration is negative, but velocity is still positive. We'll talk about that in a moment. Okay, velocity, we already found that. Okay, acceleration, let's do this next. Okay, t equals 1, t equals 2. Okay, what was my velocity again? It was 3t squared minus 9t. Or so minus 12t plus 9, right? Okay, what's my acceleration function now? Yeah, because that's going to be v prime of t. Or s double prime of t. So 6t minus 12. So just so you don't have to always write like, oh, a of t equals v prime t. I just want you guys to know that. A is v prime, or a is s double prime. That's 6t minus 12. So if I plug in 1, that's going to be -6. Meters per second squared, by the way. If I plug in 2, that's going to be 0 meters per second squared.
So at like high and low points, it's 0 always, or like on the graph, like for these types of things.
Right. And by the way, at 1, we're starting to slow down, right? Because actually stopped at 1, but but you were speeding up before, and now you're slowing down.
So it's like. You stop and you go in reverse. When you're negative.
Correct.
And you
Yes.
Start going forward again.
Yes. And we're gonna explore that in just a moment. Yes, that's correct. Where is the velocity 24? We'll just set that equal to the velocity equation. So that will be 3t squared minus 12t. By the way, I don't speak with my children in the car, just so you know. I drive very safe. Okay. Maybe. Okay. I'll go with the flow. How about that way? I keep it just I maintain a distance.
In California.
Actually, I always make full stops though, because that's a big one. I do make full stops. Yes, I do. I don't roll stop signs. And actually, I get really annoyed because I'll see someone drive really slow, and they will not stop. I'm like, what is the point of driving slow if you're not going to stop? I just get I get frustrated when I drive. Okay, I do. Okay, yes, there might be some stop signs. Okay, yes, all right. Actually, the best if you're on the Stanford campus, they do the traffic circles. That's actually the safest way to have. Way more efficient traffic circles. They don't. No, it's a European thing. I know, but yeah. All right. Now, we're looking where the velocity is 24, right? If I solve for it, I get two answers, right? One of these answers I'm going to ignore. Which one am I going to ignore? 5 or -1? Yeah, because you can't go back in time. Unless if you got a DeLorean for Back to the Future, then that could work, perhaps. Don't joke. No, but t equals 5. So that's okay. T equals -1, we ignore. And when is extortion 12? Well, we knew our extortion function was 6t minus 12. You can tell I have a lot of fun with these questions. So you get 4 for part O.
Exclude the negative ones. Can't have an acceleration.
No, you can't have negative time.
Oh yeah.
You can't negative time. The velocity extortion told me negative. 100% they can. I will say this, try not to get into car accidents because you guys are young. Your insurance will go through the roof. Get in a car accident, so be very careful. But it happens. That's why I have insurance. But try to avoid it if you can. All right. All right. So now let's look at this one. This is kind of the fun problem, and I don't know if we'll get to the rocket one. That's okay. I think we could do the snail problem. This is a good problem. I'm gonna have to minimize just a tad to kind of squeeze all this in. Maybe we'll see. We'll see how I do. Okay, so this is a velocity graph, mind you. So it's like a derivative graph. Okay. So the snail starts at the origin. Okay. It starts at what velocity? 0. Good. And we're doing inches per minute. Okay. Don't worry about the units because it's I don't have space to write them in. And travels for how many minutes?
2.
2 minutes. It's steadily increasing, right? And speeds up to what? So, it's going fast. 4 inches per minute. Oh my gosh. All right, 4. Okay. Then it stays at 2, at path 2, or whatever you want to call it. For how many minutes does it stay at 2? For 3 minutes at what speed? Yeah, 4 inches per minute. Okay, does it make sense so far? Okay, then what do you think happens at 3? Has not turned around yet. It's not turned around yet. It's slowing down. That's all it's doing. It's slowing down for how long? until it gets to what? Okay. At 0, the snail has stopped. Or we like to say the snail is at rest. That's probably the more proper way of saying it. So it's kind of like this. Turns out that's what's happening. So it goes really fast, stays the same speed. It's kind of like you're at the red light. Now it's green, you speed up, then you go kind of coast, and then you hit the brakes to slow down. Right. So say for example, trying to think here. I always like to make jokes of this. Let's say you're really eager to get somewhere, right? So you just like speed up, and then you kind of see the cops like, let me just slow down a little bit, right? I don't know. I don't think that makes any sense, but bottom line, speeding up, stays the same speed, then slows down. Now it travels in the opposite direction for how long? 6 minutes, yes. And it's steadily speeding up actually to a speed of 9. Remember, speed is the absolute value of velocity. Then it slows down to a speed of 0 at 13. At 13 is at rest again. Then after 13, what's happening now? Speeding up again. Okay. And by the way, this graph off to the right should look like this. And that should not be there. Why is that flipped? Yeah, that's a transformation, guys. Absolute value transformations. Whenever you take absolute value of a graph, any part that's below the x-axis gets flipped, as it should be, because you want all the outputs to be positive, right? So even if you're going -9 meters per second, you're breaking the law. You're speeding, you're going too fast because you gotta look at the absolute value, right? I'm gonna write this off to the margins, and then we'll fill out the stuff down below. This is very important. Oh, sorry, repeat that again. No. There's the same graph, it's just using absolute value. Okay, this is very important. You're speeding up with velocity and acceleration on the same sign. So if you're going, let's say heading towards Redwood City, that's positive direction, great. And you're going 30 miles per hour, and then you go 35 and 40, 45, and 50. So you're gunning it, you're stepping on the accelerator, you're clearly speeding up. Now let's say you see the cops, like, oh crap, it's at the brakes, right? That's actually a big tell. You should never do it. You should always let off the accelerator. But anyway, let's say you slam on the brakes. You're still moving forward, you still have a positive velocity, but now you're slowing down. Right now you're slowing down because now your instantaneous rate of change is decreasing. When these work against each other, you're slowing down. Right? That's inertia in many ways. If you think about brakes, slowing your car down. The part that's kind of confusing is going in the opposite direction, but if you think of it this way, the acceleration is working with you when they're both negative. Because now you're going in a negative direction. You can think of like wind, maybe if the wind's towards your back, or that's a different situation. But if you're going in reverse direction, but the acceleration is also reverse, it's helping you. You're still speeding up. Let's see, they're going against each other again. You're slowing down. If you have a negative velocity, but acceleration is positive, that's still slowing down. So this is how we look at through the lens of calculus, right? If your first derivative is positive and your second derivative is positive, you're speeding up. If your first derivative is positive, your second derivative is negative, you're slowing down. So whenever the first and second derivatives are the same sign, speeding up, or but if it's the opposite sign, slowing down. So let me look at notes here. So yeah, the bottom of this page here, we'll wrap things up very shortly. Okay. So I kind of already answered the bottom, the box where it says speed increases, blah, 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 speed decreases, blah, blah, blah. I already answered that for you at the bottom. But I can move the screen now. I think you guys, am I okay with moving the screen? Yeah, okay. So yeah, let me just zoom in a tad. Okay. So what intervals is the acceleration positive? Definitely from, and by the way, when we do these intervals, we'll do it as an open interval. It's kind of confusing whether you should include it. A lot of mathematicians or people who grade the AP exam, they kind of debate. We'll just keep it open. Definitely from 0 to 2, the acceleration is positive. And also from 10 to 13, I think. Yeah. When is your actually, let me take it back. I think we could be detailed about whether it's closed or open. What would I say here? I think you would include it.
It's like every number in between, right? It closes, just the whole number.
Yeah.
Wouldn't it be open?
Hold on. We're going up to what? We'll say 10 to infinity. Yeah, because you're looking at the slope of the V graph. By the way, how come I didn't include 10? What was the acceleration at 10? Is 0 positive or negative or neither? Neither, right? So that's why we don't include it. How come I didn't include 2? What's going on at 2? It's a corner, right? I can't find derivatives at corners. Yeah. Here A is 0. Here, that's a corner. And then when's the acceleration negative? From 5 to no, we're looking at the slope, not velocity, the acceleration, the slope. We're looking at acceleration. Look at the slope. The slope of the velocity graph. That gives me acceleration. No, you're slowing down. From 5 to 7, you're slowing down. Right. The velocity is positive, the acceleration is negative. Because your velocity is losing value. When you go from 5 to 7, your velocity was at 4, and it's going down to 0. So during that time interval from 5 to 7, hold on, let me finish this off. Okay, so if we go back to the graph again, right? Hold on, it's 10, yeah. Actually, you can look at your paper. And by the way, dv over dt, yeah, this dv over dt is strictly acceleration, but okay, from 5 to 7, your velocity is losing value. It's going from positive 4 to 0. You're looking at the slopes of the curve. Because what curve do I have right now? Velocity, right? The slopes of velocity is what? Acceleration. And what's the slope of 5 to 7? Negative. That's why. Yeah, don't overthink it. It's just yeah, and we do have to pay attention to those brackets. So yeah, so 5 I would not include, 7 I would not include. Yeah. It's a corner. It's a corner. Yeah. Okay, we'll stop there for today. Yeah, and I'll put homework up in a little bit. Yeah. Because use the appropriate one-side derivative. That's right. It's an endpoint, so use the appropriate one-side derivative. The right-hand derivative does exist.
endpoint's still
Right.
I get a, like, Landon gives you a grade.